Okay, this is going to be our second video in our current resistance and electromotive force series. In this video we're going to be covering sections 25.2 and section 25.3 from the text. They're closely related and I figured it would sort of be good to tie them together here, so I did them both in one video here. So let's start by looking at section 25.2. In this section we're going to be talking about resistivity. So resistivity is defined by the equation that we see here, 25.5. Our resistivity that we give this symbol rho is defined as the magnitude of the electric field over the magnitude of the current density caused by that electric field. Okay, it's going to come in units of volts per meter times amps per meter squared, so volt meters per amp. And we're going to see in the next section that volts per meter is a unit that we also give a special name to. Those are going to be ohms. And so we can see that the SI units of our resistivity, our rho, come in as ohm meters. Okay, so if we're looking at different materials, a perfect conductor would have zero resistivity, and a perfect insulator would have an infinite resistivity. Okay, and we're going to find that generally speaking, these materials that we're talking about are, well, the resistivity for these materials are temperature dependent. Okay, and the table that we see below here gives us some of the resistivities for materials we might run into. Right, so we see here we have a bunch of conductors on this side. We have some metals and some alloys. We have semiconductors over here, and then we have insulators. You can see the massive drop-off or the massive difference in resistivity between, say, conductors, which are all roughly on the order of 10 to the minus 8-ish over here, and then we can see the resistivity of insulators, which have factors of 10 to the 14, 10 to the 15. So there's roughly like 22 orders of magnitude between the resistivity of a good conductor and a good insulator. So you can really see why we choose to wrap our copper wires in whatever, like a plastic sheathing or whatever, right? Because it really will confine all current to that wire. Okay, so it's just an example of the difference between conductors and insulators when we're looking at resistivities. We also want to define this reciprocal of resistivity, which we call conductivity, as a sigma that we see here. And it's just the reciprocal of the resistivity. So sigma is just 1 over rho. Okay, and the only really important reason to do this is that sometimes, depending on where you're looking up resistivities, people will have tabulated these results either as resistivities or as conductivities, and you want to be able to go back and forth between the two of them pretty easily, right? So this table gives you resistivities, and so you could right away go to conductivities if you needed them for some calculation. Okay, so that is resistivities. We now want to talk about the temperature dependence of resistivities in different materials. So the resistivity of a metallic conductor almost always increases with temperature. Okay, and so we heat up a conductor, it becomes more resistive. Okay, and for small temperature changes, roughly on the order of about 100 degrees Celsius, we can well approximate this change in resistivity by the expression that we see here. Okay, so we have this linear expression. This is the temperature dependence of resistivity. This is our resistivity as a function of temperature. Rho naught here is some constant, which is the resistivity at some reference temperature. So we would measure the resistivity at, say, 0 degrees Celsius or 20 degrees Celsius or something, and then from knowing that, we would know the resistivity at the temperature that we're looking at by applying this equation, right? So you'd have to look up rho of 0, right, or rho naught at some reference temperature. You would have the reference temperature here, and then this alpha, this is simply a temperature coefficient that is dependent on the material that we're dealing with, right? And we can see this table down here, 25.2. This gives us some alphas for some common materials we might see, aluminum, brass, and so forth, right? So we take this equation, This would clearly be linear if we plotted it, and we simply put in the temperature that we're interested in. We have our reference temperature, so let's say for this material it was at room temperature or something, 20 degrees Celsius. So our T naught would be 20 degrees Celsius. We would know the rho naught at 20 degrees Celsius. We would know alpha for that material. We could look it up in a table, and then we would simply substitute in our T and find our resistivity at that given temperature, right? Okay, so this is our table that I already mentioned of different alphas, which are our temperature coefficient of resistivities, and so we could use those to use this equation 25.6 if we needed to. Okay, so if we plot a bunch of different resistivities over temperature for several different, and I'm not sure why this says time. This should be temperature. I'll change that. This is gonna give us the following plots. Okay, so if we're looking at a metal here, we have resistivity increasing as temperature increases, and we see that it's not actually linear, right? It does have a bit of a curve to it, but for small temperature changes, our linear approximation, the formula that we have up here, is a fairly good approximation. We can see that our line is a pretty good approximation to this curve here, and we can see that the slope of the line would actually be rho naught A, right? We can kind of see that if we change this equation into slope intercept form, we can see that the slope, the coefficient out in front of our T, our variable, is actually going to be rho A alpha, right? And you can play with that if you want to sort of prove it to yourself, but you can see here that the slope will end up being that value, and that line really is a decent approximation for the curve that we actually get when we're looking at the resistivity of these materials as a function of temperature, right? And so this is for a metal. This is the sort of plot we would get for a semiconductor. We would see that for a semiconductor, as temperature increases, resistivity decreases, right? So we crank up the temperature, and this thing becomes less resistive. Okay. And then the final plot that we want to look at here is the plot for a superconductor. We're not going to talk an awful lot about superconductors in this course, but it's important to sort of have some feel for how these things would work, right? And so for a superconductor, it's kind of interesting because as the temperature decreases for our superconductor, right, our temperature is decreasing down in this direction. As it's decreasing, the resistivity is smoothly decreasing until we hit some critical temperature, some Tc. At that critical temperature, there's a phase transition, and the resistivity drops to zero basically right away as we cross that threshold. So what does it mean to have a zero resistivity? Well, this means that once we have a current established in the superconductor, even if we don't have a driving electric field present in that conductor, even if we're not forcing an electric field into that conductor, this current is going to continue to flow indefinitely. Okay, and that kind of, we can kind of see that behavior here in this drop off, right? Okay, so that was sort of resistivity. That's section 25.2. Now we're going to move on to section 25.3. And in section 25.3, we're kind of taking these ideas of resistivity and just upgrading it to resistance. Okay, so if we look back at the equation 25.5, which was the first equation we had in our slides here, okay, and we simply write it down in its vector form. I'm just going to write it down in its vector form here because I just want to have this sort of written down if we need to refer to it later. We have this expression here. Okay, so I've rearranged it and made our electric field and our current density into vectors. Okay, and so just keep this equation 1 in mind here, and then we're going to have a discussion about ohmic materials. Okay, so for ohmic materials. And what is an ohmic material? An ohmic material is a material which obeys Ohm's law. Okay, so for these ohmic materials, rho, our resistivity, is constant and it's independent of our electric field. Okay, so this equation here is only true for ohmic materials. Otherwise, our rho is going to have some E dependence, and it's going to get more complicated, right? So we now want want to sort of change this. We've been talking about our resistivity in terms of electric fields and our current density, but we're going to find that it's often easier to talk about, instead of resistivity, to talk about resistance, and to talk about what's going on in these circuits in terms of current and potential difference. It might be easier for us to find what the current is and what the potential difference across two parts of our circuit are, rather than trying to measure what the electric field is, which can be difficult to measure, and what the current density is, which can be difficult to measure. So we're going to try and sort of translate all this into the language of I and V instead of E and J. Okay. Okay, so let's suppose that we have a conductor. Let me try and get this on screen here. A conductor with uniform cross-sectional area A. Okay, so we have some uniform cross-sectional area A that we see down here at the bottom. We have some length for our conductor L. Okay, and let V be the potential difference across the wire. Okay, so from one point on the wire to another, right? This is our low potential area, and this is our high potential area. Okay, so the current is always going to flow from high potential to low potential, right? And so we see our current I flowing from the high potential to the low potential here. Okay, and that's going to be regardless of the sign of the charge that's moving, right? We talked about that before. And we're also going to have energy lost, right? As this current is moving from our high potential to our low potential, there's going to be some energy lost, and this energy is going to be lost, transferred to ions in the conducting material as there are collisions of our current moving through this conductor, right? So it's clearly not a perfect conductor. It doesn't have zero resistivity. There's going to be some resistance for this current going through, and as there's this resistance happening, we're going to have this energy being transferred by having these collisions with ions in the material. Okay. So we want to keep this kind of image in mind for a second here. So again, I'll take another second to take a look at it. We have the current flowing from high potential to low potential. This is our cross-sectional area, our length, our potential difference from high to low. We have an electric field set up in here. We have our current density and our current. Okay. Okay. So now we're trying to build up this. Take these ideas of resistivity that we've written down in terms of E and J and translate them into the language of current and potential difference. Okay, so if our current density and our electric field are uniform, right? So if these are uniform through our conductor, then it must be true that, well, clearly our current is simply going to be our current density times the cross-sectional area, right? Our current density is defined as a current per unit area, and so if we multiply it by an area, we just get back our current, right? And so this is pretty much by definition, this equation here. This one also, right? We've spoken about how the electric field can be written in terms of volts per meter. And so if it's written in terms of volts per meter and we multiply our electric field by meters, the result comes back as volts, right? And so we end up with a potential difference, right? And so this again is pretty much almost by definition. Rearranging both of these, we can write J, our current density, in terms of current and the cross-sectional area, and we can write our electric field in terms of the potential difference over the length, right? Okay, so if we then take these two equations and we substitute them back into the sort of scalar form of this equation here, E equals rho J, right? So we have E equals rho J here. If I substitute in for the E, this V over L, we get this term here. And then if I substitute in for the J, we're going to end up with still the same rho, but our J is now going to be I over A, right? And now I can rearrange this equation to solve for our potential difference of V. Okay, so this is going to show us that for constant rho, our I is proportional to V, right? And the sort of constant proportionality that we have is going to end up being this term that we have here, right? And so we call this this constant proportionality R, our resistance, and it's going to lead to these two equations that we have here. Okay, so here we're simply taking this last form of equation 3. We've moved I over here, and we've relabeled rho L over A into R. Okay, and so we have that sort of expressed here. Our resistance of our conductor can be written as the resistivity of the conducting material times the length of the conductor divided by the cross-sectional area of that conductor. So that's our resistance, and the relationship between resistance, potential difference, and current, which rearranging this equation here can be written like this: V equals IR. This is often what people will have seen in previous physics courses referred to as Ohm's law. And so we have this relationship now, right? We have the voltage or potential difference. Voltage is just another way of saying potential difference. Is equal to our current in our conductor times the resistance of that conductor. Okay. And so the SI units for our resistance, as I mentioned above, is going to be written as ohms, and ohms are just volts per amp. Okay, and we can kind of see that when we express it in this way, right? We have volts and we have amps, so it's going to be volts per amps is going to be our resistance. Okay. So now let's take a moment to sort of think about what's going on with resistance. And we remember just from a moment ago that because resistivity is a function of temperature in general, our resistance, well, we should expect that our resistance will also be a function of temperature, right? It makes sense that it would be a function of temperature, and it turns out that that is the case. We see that expressed here in expression 5. So we have our resistance written down as a function of temperature. Again, we would have some resistance at some base temperature that we would know, right? So we would have some temperature at which we've measured the resistance of our resistor or our conductor or whatever we're trying to measure the resistance of. And then we would simply have this as a function of t, right? So this would be the linear relationship again, which would be a good approximation for the actual resistance of our conductor. And again, alpha is simply those coefficients that we had in the table above. Those aren't different from resistivity to resistance. Okay. So here, what are we saying here? Basically, this is just what I said as I was describing equation 5. We just have our R naught, right, which is at some temperature T naught that we've measured, and then we can sort of extrapolate out what our resistance at some given temperature will be. And R naught is often measured at either 0 or 20 degrees Celsius, kind of room temperature or whatever. And so we can get our temperature-dependent resistances from this linear expression if we need to. Okay. So I'm going to make a note here. There's a couple of things that the textbook does that I'm not going to talk about here, but that could be useful to you if you're having specific issues or if you're curious about some of these things. So the first thing I want to note is that the text goes into a sort of discussion about an analogy that it draws between the flow of water down a pipe and the flow of current down a wire, and sort of how you can think of resistance in these terms. So it's a decent discussion, but I'm not going to have that discussion here. But if anybody's having sort of conceptual issues thinking about how resistance might work, that might be a good read, so to give that a look. Also, the textbook goes into a discussion about the labeling scheme for sort of off-the-shelf resistors, like resistors you could buy at a store, right? So you could go in and buy certain resistors to build an electric circuit. And there's a sort of color coding system for how those all work. Anybody that might be going into a field where you're going to be handling these resistors, it might be a good idea to go give that discussion a little bit of a look. It's kind of a cool coding system that they've come up with, but we're not really going to look at that in this course. So I kind of leave it as side reading if you guys are interested in looking at that. Okay. So we're going to sort of leave those two there, and we're going to move on to a further discussion here. So for ohmic resistors, this is again resistors that follow Ohm's law. The graph of our current as a function of voltage is going to be a straight line, right? That's what we see down here. Okay, and so the potential difference is going to be, well, I mean, we can kind of see everything that we need to see from the plot here, right? We can see that that as our potential difference gets increasingly positive, we have an increasingly positive positive current, and as our potential difference is negative, we have a negative current, and it's linear. We can see the slope is 1 over r here from our Ohm's law thing, right? V equals IR, right? We can see that would be our slope. Okay, so I'm going to erase that to clean up the notes. Now, we can also look at what these plots would look like for non-ohmic resistors, right? Let's say we had a graph with current as a function of voltage that we see here. We can see that this is nonlinear, right? And it can also depend on the direction of the current flow. So we can see first that this is nonlinear. We have this sort of exponential behavior here in the positive potential difference area, but we also have this sort of strange linear behavior here. And what is this sort of showing us, right? This is kind of showing us that for positive potential difference, we have increasing amounts of current flowing, right? So we crank up the potential difference, more and more current is flowing through our conductor. But as we crank down the potential difference, and as we move into negative potential difference, we have the same current flowing no matter how high in the negative direction we crank up our potential difference, right? And so this is interesting. This behavior, this sort of a plot here, is what sort of describes what we call a semiconducting diode. Okay, and so for positive V, our anode, so the anode and the cathode are two different ends of our diode, right? So for positive V on the anode side of our diode, and for lower V on the cathode side of our diode, I increases exponentially as we crank up V, right? So we have this sort of material that if we have high potential on one side and low potential on the other side, and we crank up that potential difference, we get more and more current flowing through our diode. But if we now flip it so that we have negative potential difference, i.e. we have like a lower potential on the side that we used to have the higher potential on, and vice versa on the other side, then we see that there's very little current flowing backward in the other direction. Okay, so for positive V, current flows in the positive direction, but for negative V, almost no current flows in that negative direction. So the diode, this sort of material that acts in this way, this diode would give us a sort of behavior of a valve in a circuit, right? It would allow current to pass through in one direction, but if something were to happen and the potential difference were to switch, our current would not be able to flow back through in the other direction, right? So it's kind of like a valve in a sort of water or fluid situation, right? So that's just a quick look at diodes. And now what we're gonna do now is move on to the sort of two examples they have in the text. They only really have two examples at the end of section 25.3. They didn't do any examples in section 25.2. So I'll do these two examples. If we find that there are more questions, I can always address this with an additional example at our Wednesday meeting. But for now, I'll focus in on these two examples. I have numbers worked out over here, so I'll pull those up. And so we'll start off by looking at example 25.2, and this is from section 25.3 in the text. So we're looking at electric field, potential difference, and resistance in a wire. Okay. So we have the 18 gauge copper wire that we looked at in the previous video. It has a cross section of 8.17 times 10 to the minus 7 meters squared. We looked at that, or we found that number as a sort of intermediate result as we were doing the calculation in the previous video. It carries a current of 1.67 amps. And we want to find the electric field magnitude in the wire in part A. In part B, we want to find the potential difference between 2 points in the wire which are 50 meters apart. And then in part C, we want to find the resistance of a 50 meter length of this wire. Okay. And so how would we do this? Well, we'd start off in part A. What do we need? Well, we need to find E, right? So if we want to find E, well, we can use this equation 25.5, which we saw at the beginning of these slides. 25.5 simply says that rho, our resistivity, is equal to our electric field over our current density. Okay, so rho is equal to E over J. We can rearrange this to give us E equals rho J. Okay, and so we also, well, so we have this expression here. We want E, right? And we have this expression here. We know what I is, but we don't know what J is. So it would be nice if we could write J in terms of I and maybe A, right? If we could write our current density in terms of our current and our cross-sectional area. Well, we can do that if we look at equation 2 from above. Equation 2 from above gives us J equals I over A. And it was kind of just a discussion of how this almost had to be by definition, right? So if we combine these two equations that we see here, we end up with E equals rho I over A. And now it's just a matter of substituting in numbers. Okay, we would look up rho from table 25.1. So we have a copper wire here. Let's go to table 25.1. It's going to be up all the way up here. So for copper, we have this 1.72 times 10 to the negative 8 value. So we're going to plug that in down here. And so we have, for rho, we have 1.72 times 10 to the negative 8, and that comes in at ohm meters. I'll write down the units for now. We're given our current. We know it's 1.67 amps. And then this is all over our area, our cross-sectional area, which we're also given 8.17 times 10 to the minus 7 meters squared. Okay, if you do that calculation, you will find, and maybe I'll put the result here, you will find that this gives you 0.0352 volts per meter. Okay. And so that's the magnitude of our electric field in this conductor, and that's what we're looking for in part A. In part B, we want the potential difference between 2 points in the wire 50 meters apart. How would we find that? Well, in part B here, we're simply going to use equation 2 again, but the other part of equation 2 that we wrote down, where we have V is equal to EL, right? And now it's just a simple matter of substituting in numbers. We just calculated E, so I can put in E. Oops, that's a 0.352 volts per meter. And our length of the wire, that's just 50 meters. Okay, if you do that calculation, you're going to find 1.76 volts. Okay, so that's the potential difference between 2 points 50 meters apart on this wire. Okay. In part C, what are we looking for in part C? We're looking for the resistance of this 50 meter length of wire. Okay, and so we can use our Ohm's law or our equation 25.11 here from above. This simply tells us that V is equal to IR. We can rearrange this to get R equals V over I. And now we just substitute in numbers. We know, we just calculated what V was, and we're told what our current is. And so if we do that calculation, we end up with 1.05, and this would be volts per amp, but we know that volts per amp can be written as ohms now, right? So that's our R. Okay. I'm just going to take a quick moment here and pause this and save this before we lose it, and I will continue with the next example. Okay, let's keep going. Now in example 25.3, again of section 25.3, we're going to be looking at the temperature dependence of resistance. So we're going to start off by supposing that we have a copper wire with a resistance shown here at 20 degrees Celsius, and we want to find the resistance at 0 degrees Celsius and at 100 degrees Celsius. Excuse me. Okay, so this is pretty straightforward. We're going to use equation 5 from above, which I'll rewrite here. We have our resistance as a function of temperature. This is going to be equal to R naught, right, which is our resistance at some reference temperature. 1 plus alpha T minus our reference temperature. Okay, and so we're going to have to look up a few values here. We're told, well, so for the first one we want to find R at what is it? Or hold on. Why is it 20 degrees? Okay, so we want to find R at 0, right? So we're going to find R at 0, and we're told what our resistance is at 20 degrees Celsius. We need to look up what alpha is for our copper wire, and if we scroll up, we're going to find our alpha again. That's going to be this value here. We need our temperature that we're looking at here. So our temperature that we're looking at here is 0 degrees, and our reference temperature, that's 20 degrees. Okay. And so if we do this sort of calculation, it's fairly straightforward, right? So this value is from table 25.2, and if you do this calculation, you're going to find that R of 0 is actually 0.97 ohms. Okay. So that's our resistance at 0 degrees Celsius. Now we want to find the resistance at 100 degrees Celsius. And so this is just a matter of substituting in the right numbers again. We're going to end up with this expression here. Oops. Okay. And now we're going to have, instead of the 0 degrees Celsius, we're going to have 100 degrees Celsius minus 20. And if you do that calculation, you're going to end up with a 1.38 ohm resistor, right? So this is our resistance at 100 degrees Celsius. Okay. And so what do we sort of see happening here? Well, first of all, this is the answer to the question, right? So this is all that we were asked to do. We have our resistances at 0 and 100 degrees Celsius. Those are the resistances, and we're done. And sort of, can we double check that this makes sense? Well, yeah, we can, right? We know that as temperature is going up for a conductor, we expect that our resistance will go up, right? So temperature goes up. This implies that resistance goes up for any conductor, right? And so we're dealing with copper here. We expect this to be the case. And do we see that? Well, yeah, at 0 degrees, we saw a resistance of 0.97, and at 100 degrees, we see a resistance of 1.38. Okay, and so we do see that behavior. Okay, so we'll leave these topics here from section 25.2 and 25.3 here, and we'll move on to new stuff in the next video. I will see you guys there.